So today we're going to be introducing the idea of what a tree is, and then we'll kind of whittle it down even further. So we're going to have to go through some tree terminology so that we can understand what a tree is. I'm not going to be getting overly formal about it at this stage, but I need you to understand the main gist of what a tree is. So what we need to focus on, at least for us, because I want you to understand that this idea of a tree, it's not just like the trees outside, okay? So we're not talking about the trees outside that you can go climb up if you feel like you're a little bored. Just don't hurt yourself, okay? So these are a tree. A tree is an abstract model of now this is the fun word, hierarchical structure. I'll address what I mean by this word hierarchical if you've never seen this word before. Don't worry, we'll talk about it. So it's worth noting, and why I'm especially interested in talking to you about trees. And again, I'm not talking about the ones outside. In fact, the ones that we're going to talk about often are drawn upside down, where we have this thing called the root that's at the top, and it's drawn downwards from the root. Namely, we're going to be interested in what we're called rooted trees. Trees frequently occur. They frequently occur in data structures. And algorithms. Now, I'll explain why in a moment. Often do due to their fascinating properties. So you could study trees as a structure itself, like an object, but within the domain of data structures, as I'm going to show you at some point, data structures often, this concept of a tree will pop up often if you want to come up with a structure that makes for efficient queries, insertions, removals of data, for which parts of the tree will store data. And naturally, you may want to do things with this tree. So for example, you want to store some data for some application. You may put it in this tree, and the tree will store it at what we call nodes or vertices, depending on the context. In the larger context of algorithms, the structure of a tree sometimes occurs in all sorts of different ways. For example, the computations themselves, as executed, take the form of a tree. Or perhaps it may be that the structure of itself, so there might be something that the algorithm constructs that looks like a tree, and maybe the properties of trees can tell us something about the efficiency of that algorithm, for example. Now, you don't have to be so fascinated about these things just to get excited about trees. Trees occur very often in societies, because societies tend to be interested in hierarchies. That's where the fancy term comes from here. Some examples of trees. So let's talk about a couple examples of trees. Now, for those that are a little bit more tech literate or maybe interested in technology, say on a computer. The first example I'll draw up is a file system. Now, if you use a computer, you very often may be familiar with the idea that if you have, say, a drive on your computer, it's broken into what they call directories, meaning that as you navigate the file system, you end up with different folders, and those folders are often contained in other folders, causing you to have it so you can navigate from part to part to part to part of a tree. And this tree, again, remember, it's not like this, it's going to look like this. will be the navigation of, say, folders or even their indices for when they are stored. But I'm not going to get into the technical know-how of that, but you could think of it like that, where the root directory, that term comes from to talk about trees, often is where those directories start. One that occurs very often in societies is an organization of a company. So this could be a company, it could be, say, some sort of structure that involves where people talk to each other, but the organization of a company is one example. So, for example, you could have something that looks like this. Maybe you have a company called Compute and Company. And say this is the main organization for which it is broken into different divisions. It has a sales division. Perhaps it has a manufacturing division. Perhaps it has a research division. So these are different divisions of Compute and Company. So you could think of how you break the organization down into these different levels as parts of the hierarchy for which the company exists. So, for example, the sales division could have one in Canada, as an example. It may have an international branch. It could, in manufacturing, maybe because it's a computer company, perhaps they manufacture laptops, and maybe they manufacture desktops. But more importantly, these can be broken into several levels. They don't have to all be broken by equal components, for example. For example, the international branch may have multiple parts. Maybe they have a UK branch. Maybe they have a USA branch. Perhaps even they have a branch for Candyland. Don't ask me where Candyland is exactly. Just try to keep it fun, okay? So keep in mind that Candyland, this office associated with international sales, is a part of the sales of the company, for which that company is Compute Company. So to get the idea is that you could model many different hierarchies using trees. These are examples of what we call rooted trees, for which we would often refer to this guy up here as the root. But that's an idea of what a tree is. I need to give you some tree terminology so that we understand what we're talking about here, because it's really important we had a little bit of a blip there. So it's really important that we have some discussion about how we're going to talk about these trees. So we're going to talk about some tree terminology. And if you don't have this terminology, it's going to be very difficult to talk about these things. Just as with most discussions with the dreaded M word, the mayonnaise. It's going to become rather difficult to talk about a subject without having clear and exact terms for what we're talking about here. So I'm going to try drawing out a tree. So I'm going to label this one A. Kind of like my computing company over there. I can talk about these things. I'm writing these circles down, each with different parts. So I have B, C, and D. We have, think of these like our different parts, kind of like the company over there or our file system. We have E, F, and then maybe there's something like I, J, and K. And maybe we have G and H. Now, you might ask, Dan, do these letters matter a whole lot? Not necessarily. These are just labels that I'm using to talk about the tree. So notice that this tree is it's pretty similar to this one I have over here on the left side. They're pretty similar. Now, I want to go through some terminology. So we're going to focus on what are called rooted trees. They get that name because we designate a special one of these circles, which we keep in mind that the shape of them, it doesn't matter anything. This is just more about the structure of it. These labels, they're labels I've prescribed to them. These things are called nodes, and these connections are called often edges, links, or arcs, depending on the context. So we're going to focus on rooted trees, but we call it a rooted tree because there's going to be a special node. One of these guys is going to be called the root node. And if having a root dictates that there's going to be a relationship between the nodes that we're going to talk about here in a moment. So a rooted tree is given here. That's an example of a rooted tree. This is just one example of many trees you could make. So I need to talk about the terminology. So as I've alluded to, kind of like our compute and company example, I'm always going to draw these trees. Notice that the trees are not drawn like this. They're drawn like this. That's typical. It doesn't necessarily mean anything special. It's just something that is very common among people that draw rooted trees, is that the root node is typically at the top. So we call this the root node, or sometimes it's called the root vertex, but I'm going to try to use the term node when talking about trees specifically, just to make it so it's a little easier for us to discuss. So sometimes this is called, so A, for example, is the root or root node. As again, like I said, all of these circles with labels on them, and remember the labels themselves aren't intricate or deep needed for what a node is. This is just something helpful for us to talk about. Call that a node. And these connections over here, these things are called often edges. That's an edge. Sometimes they're called a link. Sometimes they're called an arc. It depends on the context. I'm going to use the phrase edge, but it must be stressed that there is a special relationship a rooted tree has for which these edges are defined on. So there's a broader context. People use this phrase edge involving what is called graph theory. It's because rooted trees are special kinds of trees, and these trees are called graphs. And so the big thing you really want to know about this rooted tree, by having a root like this, nodes have a parent-child relationship. So this is going to be really important for our discussion. We have a parent-child relationship. So that parent-child relationship is dictated by where the root is designated. So this is a designated node. We call it the root. And we want to think about it as we go downward down the tree, kind of like talking about this like in many different settings. Like another good example of something like a tree, for example, you could think of the history of a family, for example. So this can be the first ancestor, and for which there are children of that ancestor. You could say, for example, that A is the parent of B, but it also is the parent of C, and also the parent of D. Likewise, you can talk about the children of A. So the children of A are B, C, and D. So they're going to have parent-child relationships. These are dictated by this parent-child relationship. Is that clear to everybody? So just as like, so just to clarify, so like A is the root node in this example. And I want to ask you a question. Which nodes are the children of B? Which ones are the children of B? Well, B's here. There's an edge that goes from B to E, and there's an edge that goes from B to F. So that means that the children of B are E and F. But what about the parents? So if I were to look at node E here, what can I say about its parent? Well, its parent is B, right? So B is the parent of E and F. So there's this parent-child relationship that is imposed when we can discuss things like the root node like this. So do note that the root itself being dictated where it is can change how we think about these parent-child relationships. So for example, if I decided E was the root node, then I would now keep in mind, the drawing of the tree is not terribly important. The drawing is very helpful for us to understand the parent-child relationships. The way you want to think about it is, if you have the root, everything draws away from the root. So the children of A are B, C, and D. But if, say, for example, E were the root, then you could say that, okay, well, even though it looks like this, the child of E would be B, and the parent of B would be E. So do note that this is just helpful for us to draw them like this. But it's worth noting that root has a very special property for which we think about these hierarchies that are how we think often about rooted trees in this context. So if it makes it easier for you to think about, sometimes people will draw arrows on the tips of these just to help remind them that it's parent-child, parent-child, parent-child relations. Now, there's other terminology that exists, such as siblings. So for example, if you have two children of the same parent, if, for example, E and F are the same children, are children of B, we could call these siblings. So like, again, you can think of it like ancestry, for example, you know? That's where a lot of this terminology comes from. So that's another term that's used. I'm not going to be talking so much about siblings here, but I just wanted to point that out. But again, I just want to remind you that we're going to care a lot about this idea of a parent. We're also going to care about what a child is and how many we have sometimes. So, for example, B, C, and D are children of A. But now there's another notion that we need to be wary about. Just like ancestry, you can also have descendants. So for example, you can argue that because we have parent-child relations between A and C, and from C to G, then it has to be that a descendant of A has to be G. In fact, you can call that a grandchild, right? Because this A would be like the grandpa or grandma of G. So we call that the grandparent, for example. But we could talk about the idea of descendants of a node. So for example, what are the descendants of B? What are the descendants of B? Well, think of it. These are all of the descendants of node B, meaning that they are children, children's children's, children's 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 of B, and so on, right? So in this case, the descendants of B would be E, F, I, J, and K, right? But this also means that I can also talk about ancestors. So this one's going to be relevant for us today. But it's worth noting that if I give you a node like J, you'd agree with me that J's parent is F, F's parent is B, and B's parent is A. So all of these nodes are ancestors of node J. So we could say that A, B, and F are ancestors of J. Does A have any ancestors? Does A have any ancestors? Do you see any, does the root have any parent? No, it's a very special node in that sense. Because the way we've defined the parent-child relations with this root node in mind, the root doesn't have a parent. So notice that that's something you always can know about the root node, is the root node has no ancestor. A has no ancestors. That's true for any root node. Okay, so just please take that little piece of knowledge, put it behind your ear, because sometimes it's actually really helpful for us to use. Now, there's some other terminology I want you to be aware of for what we're going to be discussing today. I'm going to include in the notes some more terminology, but the ones that we're going to be most interested in today, first we have this idea of an internal node, or we would say that the node is internal. So an internal node, these are nodes with at least one child. So a node with at least one child. So can somebody tell me where are the internal nodes in this tree, for example? Which nodes are internal nodes here? Well, let's look at the definition here. Okay, so A has at least one child, so most certainly, so example, we know for sure A is an internal node because it has at least one child, right? In fact, it has 3, right? It has B, C, and D. Is B an internal node? Well, let's look at the definition. It says there has to be at least one child. Well, notice that B has 2 children, right? So most certainly it is also an internal node, or is internal. How about C? C has 2 children, right? It has 2 children. So C most certainly is internal. How about D? Is D an internal node? It doesn't look like it. It has no children. We'll have a special name for these in a moment. But how about E? E has no children, right? So most certainly is not internal. How about F? Let's think about it. It certainly has ancestors, but has descendants, implying that there is at least one child. So it in fact has 3. So most certainly F is an internal node. So you might ask, okay, so what are the nodes, like what do we call the nodes that aren't internal? Now, in the spirit of thinking about a tree, like a tree outside, these are often referred to as leaf nodes, or leaves as plural, or a leaf singular. So a leaf node, or sometimes these are called external nodes. I will not use this phrase, but if you ever wonder what an external node is, that is also a name for a leaf node, or leaf. So what is this? Okay, well, if an internal node is one with at least one child, then this most certainly has to be one with no child. A node with no children. Right? It's a node with no children. So, for example, node D, that is a leaf node. E, that is a leaf node. I, J, K, G, and H, these are all leaf nodes, or leaves. So we call a singular one a leaf, or a leaf node. Plural is leaves. So these things are probably the most important things to be aware of. But it's worth noting that there's a few other terms that I want us to be aware of, and we're going to use some of them. Okay, so let's talk a little bit about them. So the first thing I want you to be aware of is something called the depth of a node. So the depth of a node. So this is sometimes also called its level, or the level of a node. So is the number of ancestors. The number of ancestors. So we could talk about, so this pertains to nodes. So I could give you a node, I could tell you about its depth or level. So first thing I want to point out is that every node in a tree has a depth. So it's dictated by the number of ancestors. So for example, the root. We already established it has no parent, hence it has no ancestor. We would agree that the level or depth of A is 0, right? Likewise, notice that B, C, and D, these all have one ancestor, right? You'll see why we draw them like this, where we kind of lay them out level by level like this, so it's easy for us to identify the levels of the tree. That's one reason why some will draw trees like this, where the root is at the top and the children and descendants follow downward like this. So likewise, you can look at E. How many ancestors does E have? Can somebody tell me how many ancestors that E have here? Well, it has 1, 2. It has 2. Likewise, F does as well. G also has 2 ancestors. H has 2 ancestors. So notice that there's something interesting going on with our drawing. So it isn't just by happenstance I drew it like this. This is very common. So you could do the same thing with node I. Well, has 1, 2, 3 ancestors. Notice all of the nodes on this level of the tree have 3 ancestors, hence the level is 3. So take notice that the number of levels I have in total is 4, because the 0th level is a level. So you can talk about the level of a node. So there's a level of a node, and there's also levels of the tree itself. So please keep that in mind. It isn't just simply that a node has a level. You could talk about levels of the tree, and sometimes that's actually really helpful to talk about. A related concept is called the height. The height of a tree. So the height of a tree is the maximum depth of a node. A node in the tree. So what's the height of this tree then if it's defined by the maximum depth of a node? What are the deepest nodes in this tree? Sorry, I got really excited here. Can somebody tell me a node with the maximum depth for this tree? Is it this one? Is it E? And I don't think it's that one, because it has depth 2, and we know there's nodes with depth 3. So let's pick one of these. So I has depth 3. J and also K do. There's none that have a higher depth. So what's the maximum depth of any node in this tree? It is 3. So our tree has height 3. So you'll notice that there's a clear relationship between the number of levels and the height of the tree. Does anybody see it? So this is something to keep in the back of your mind, because sometimes it's easy to confuse the number of levels of a tree and the height of the tree. Well, we know that I'll give you a moment. Well, look. Okay, we know that the level, so there's a level of 0, 1, 2, and 3, but we know that the number 3, for example, just for our example tree, this could be any other tree. Remember, like Compute and Company, it could be a tree that looks like this. In fact, it doesn't necessarily even have to have labels. So here's another tree. Here's another, in fact, I can make another tree. There's another tree. It's rooted when I dictate a node is a root. So that's another tree there. What's the height of this tree? Well, we find a node with a maximum depth. So notice that we have one of these guys down here. So it has 1, 2 ancestors. So the height of this tree is height 2. How about what would be the height of just a tree with one node, just the root node? What would be the height of that node? Sorry, that tree. Remember, the tree only has one node. Well, it has no ancestor, so the height is 0. It's 0, right? So we're going to presume, by the way, that trees have at least one node typically. There's some funny conventions around what you do with a tree that's what we call empty. We're going to presume our trees are non-empty typically, meaning that there's at least one node. So now that we have this idea, so has anybody figured it out yet? The connection between height and depth? So namely the number of levels that we're talking about. Number of levels in the tree versus the height. Well, I already told you that this is technically the first level of the tree, right? So, but it's level, these are nodes all have level 0. So they are level 0, meaning they have no ancestors. So it's one higher than the height. So the number of levels is always one higher than the height of the tree. So just keep that in mind at all times, because it's very easy to forget that. And it's easy to confuse height with number of levels. The number of levels is always one higher than the height, because the height itself is that it is the one with maximum depth, right? It's a node with maximum depth, but remember, we start at level 0 in the tree. So just keep that in mind. So next, sometimes it's actually really helpful to talk about what we call a subtree. So this is just simply a tree consisting of a node and its descendants. Its descendants. So for example, if I wanted to talk about a subtree, now keep in mind, a tree itself can be its own subtree if you consider the node that is the root node. So for example, the subtree of A would be all of this tree. The subtree of node C here is this tree. The subtree of F looks like that. It's only that part of the tree. The subtree of B would be B and its descendants, right? That's what we've defined it as. So it would look like this, right? So sometimes it's helpful to talk about parts of the tree. That's where the subtree definition is helpful for us, okay? Next, we have this idea of an ordered tree. Now, this is going to be highly relevant for us today. So an ordered tree is where the children of the nodes are ordered. So for example, if we're talking about what we're going to see later on called a binary tree is an ordered tree for which we're going to designate a left child and possibly a right child. So possibly in each case. So you may, for example, impose an ordering on the children so that they have special properties. So for example, it might be that their labels mean something, or perhaps their children are given special names, and for which you're supposed to always interpret them in that order. There's some ordering. That's the whole idea. So as an example of such a thing, we're going to see it's called a binary tree. Binary tree is an example. So typically we're talking about a rooted binary tree when we talk about that, because otherwise we don't have parent-child relations. Unless you decide you want to impose them. I shouldn't be too restrictive on what people can do with trees. Lots of things you can do with a tree. Other than planting them outside, okay? So we have an unordered tree. So the children of the nodes are unordered. So just as a hypothetical here, suppose that this tree, there was a special meaning for that B comes before C because they're letters in the alphabet, say the English alphabet. Perhaps I've dictated that the children, like this is an ordering of the children based on the letters, like in the alphabet. Like B comes before C because B comes before C in the alphabet. Likewise, you'll notice the same thing is true actually on all these levels. But if I switched, say, a couple of these around, like I and J, that may not make it ordered in that hypothetical example. But with that being said, this is some tree terminology that we're going to use. And once we have that in place, now we can prove some fun properties. So just remember that it's not just this, it's not compute and company only, it's not just this tree. We're talking about there's this idea we have this structure of nodes, and the structure of nodes have it where we have a root node, because we're going to talk about rooted trees here, for which we have descendants that are dictated from parent-child relations, such as over here, like this is the root, this is the child of this node, this is the child of this node, and so on. And we draw them from top to bottom. Typically, this is helpful for humans to think about the trees, often because we like to organize them by level of the tree. Is everybody getting excited about trees? I know I am. So this is just some terminology to talk about trees.